In the previous lecture, we have discussed the line equation of a transmission line. In fact, we have considered the two parallel line transmission line and obtained the line equations. When you say line equations, we have seen basically those line equations were the second order differential equation in terms of the voltage and the current. Okay, we have seen that this left side of this circuit is actually the generator end, or it is also called sending end, because we actually connect a source or you can say alternating source or a source of electromagnetic wave between these two terminals. And this is the load end, or it is called the receiving end in right side, where our signal appears. Okay, and measuring the distance from the sending end, we have obtained the expressions for V of x, that is voltage as a function of x, and I of x, that is current as a function of x. And those equations which we have obtained in the previous lecture, that will be needed in this second lecture. Actually, in this second lecture, our prime aim is to discuss a very important quantity that is called reflection coefficient. We have seen actually earlier that when you obtain the equation for V of x and I of x, actually that represents the incident and the reflected waves. So corresponding to the incident and reflected wave, we actually define a very important parameter that is called reflection coefficient. So prime aim of this lecture is to discuss the reflection coefficient. But before knowing about the reflection coefficient, you will have to learn regarding the concept of incident wave and the reflected wave. And that will be discussed actually in two headings. First of all, we are going to see how the voltage and current are related with the distance from the sending end and from the load end. Okay, separately, first of all, we will discuss these two things, and after that we will define the reflection coefficient. Since we will need the line equations for this discussion, so I have mentioned here the two final results of the previous lecture. We have seen that V of x, that is voltage as a function of x, where x is measured from the sending end or the generator end, that is given by A times e to the power gamma times x plus B times e to the power minus gamma times x. And similarly, we have also obtained the equation for I of x, that is given by 1 over z naught times this much. These were our final results of the previous lecture. You know, in these two equations, A and B are arbitrary constants, or you can say these are actually the integration constants, because when the original differential equation obtained in terms of V and I, which were actually the second order ordinary differential equation with constant coefficient, these two A and B appear as the integration constant. And you know, definitely these integration constants will be obtained by applying the proper boundary condition. So in this lecture, we will see how these constants A and B can be obtained. Okay, and gamma, which you have seen earlier, that this is given by the square root of the product of Z and Y, where Z is actually the impedance and Y is admittance of the circuit. And you know, this Z is given by R plus J omega L. Okay, in fact here J is actually the imaginary, that is a square root of minus 1. Okay, and this y is given by g plus j omega c. Here g is the conductance, c is capacitance, and omega is actually the frequency of the alternating voltage or current. Okay, and this gamma is actually known as propagation constant. In fact, if you are talking about a wave, definitely the wave equation, the equation which represents the wave, must contain two parts. The first part must be its amplitude and another will be its phase factor. So actually this gamma is in general a complex quantity, and you will see later on in this present lecture that we will represent this gamma by alpha plus I beta. You can also write alpha plus j beta. Okay, alpha plus j beta you can write, because the symbol I or j both stands for the iota, that is imaginary. Okay, in fact later on I have used the symbol I instead of j, but in previous lecture I have used the symbol j for imaginary, so I have written it here. And you also know that this z naught is what? You have seen in my previous lecture that this is a square root of the ratio of z and y, that is ratio of the impedance and the admittance, that is a square root of r plus j omega l over g plus j omega c. And this z naught is known as characteristic impedance. So these were our result of the previous lecture. In fact, in this equation, this term b times e to the power minus gamma times x, actually this represents the incident waves which travels from the sending end to the load end. Okay, you can see here I have mentioned here, this is the this is the sending end or the generator end. You can say this is your generator, that is source, and this z naught represents the characteristic impedance, and this zl represents the load impedance. Okay, over which our output appears. Okay, so this term b times e to the power minus gamma x, this actually represents the incident wave which travels from sending end to the load end. And the first term in that equation, that is a e to the power gamma x, this represents the reflected waves. And this reflected wave, you can see, travels from the load end to the sending end or the generator end. Okay, or the source end you can also say. Okay, now as I have told you, we will actually find the value of a and b, that is the unknown constants, by applying the proper boundary condition in two cases. First of all, we will measure the distance from the sending end. It means we will consider the x coordinate of the sending end equal to 0, and as we will move along the x-axis, because you have seen in previous lecture that the two wires of the transmission lines have been considered lying along the x-axis. Okay, so if you consider that there is a point P here and its distance is x from the sending end, then as a function of x, what will be the value of v and what will be the value of I? First of all, we will find. Already you have obtained that v of x is given by this and I of x is given by this. But since in these two equations we do not know the actual value of a and b, so our aim is first of all to find these two unknown constants, and that will be evaluated by applying the proper boundary condition. Okay, so let us see. First of all, we are going to find the value of a and b, or we are going to relate the voltage and the current to the distance measured from the sending end. Okay, and in this case what will be the boundary condition, and how applying that boundary condition, how we can find the actual or proper value of A and B. You can see, when at the sending if you are talking about the sending end, as I have told you, you have to take x equal to 0 at the sending end, and in that condition our current will be equal to Is. Here the subscript S actually appears for the source or for the sending end. Okay, and the voltage at the sending end is equal to Vs. Okay, and therefore you can say that this Vs will be equal to Is times Zs, where Zs is actually the impedance of our source. What is this Zs? Zs equal to impedance of source. Okay, impedance of source. So at the sending end, the voltage between these 2 points, that is this point and this point, will be equal to what? That is equal to Vs, sorry, not this point, but this point and this point. In fact, we consider that our source has an impedance Zs. Okay, and it sends a current Is. So Is times Zs, in accordance with Ohm's law, this will be the measure of this Vs. Okay, now actually we will apply this condition, that is at x equal to 0, I is equal to Is and V equal to Vs, where Vs is equal to Is into Zs. This boundary condition now we will apply on our basic equation A and B, which we have mentioned here, and this equation we have seen in my previous video. Okay, so let us see, when you will take x equal to 0, see here, then e to the power 0, that will be equal to 0. So in RHS there will be only A plus B. Okay, and you have seen, we have considered that at x equal to 0, this V is equal to Vs. Okay, V equal to Vs. So when you will apply that boundary condition on this equation A, your result will be what? Your result will be Vs equal to A plus B. This is just a very simple calculation. And again we will apply the same boundary condition on the current equation, and you have seen that actually the current equation is I of x is equal to 1 over Z0 times A e to the power gamma x minus B e to the power minus gamma x. Now apply this condition. When you will take x equal to 0, again these two exponential factor will be 1, because e to the power 0 will be 1, and I will be equal to Is. So I have written here, you can see Is will be equal to 1 over Z0 times A minus B. Okay, and so by taking the cross multiplication, you can write Is times Z0 equal to A minus B. Now you can see we have actually two independent equations containing A and B. In equation 2, you can see that A minus B is equal to Is times Z0, and in equation 1 there is A plus B equal to Vs. So if your aim is to find A and B, what you will do? The algebra is very simple. When we will actually add equation 1 and 2, first of all see the RHS. When you will add A plus B plus A minus B, A minus B is the RHS of equation 2. This B will cancel out, and this sum will be 2A. Okay, and in LHS there will be Vs plus Is times Z0. Okay, so you can see after adding equation 1 and 2, we simply get 2A equal to Vs plus Is times Z0. But you have seen that this Vs is equal to Is times Zs. Okay. So finally we get A equal to Is over 2 times Zs plus Z naught. Okay. So in this way you can see how easily we have obtained the unknown constant A. Now in the similar manner, when you will subtract this equation 2 from equation 1, then you will see A will cancel out and you will get B. Okay. And so in this way, after subtracting equation 2 from 1, you can see B will be obtained, and that B will be equal to Is over 2 times Zs minus Z naught. Okay. So in this easy manner, we have obtained the values of constants A and B. After obtaining these two values, that is values of A and B, now you can find the actual value of V of x. How this V varies with x, now we can actually find. You know, V of x, this is equal to A times e to the power gamma x. But you can see A is equal to Is over 2 times Zs plus Z naught. So A has been replaced by this. Okay. And plus B times e to the power minus gamma x, but B is this much. So now you can see V of x is equal to this much. Now let us simplify the RHS of this equation to some extent. First of all, see this term Is times Zs, first term of the both terms. So when you will take the first term of this and first term of this, you can see in that condition Is times Zs divided by 2 will be a common factor, and the remaining terms will be e to the power gamma x plus e to the power minus gamma x. So you can see I have written here V of x will be Is times Zs, this is a common factor, and there will be e to the power gamma x plus e to the power minus gamma x over 2. Now see the remaining term. This is these are the remaining terms you can see, and you can associate these two terms. In fact, here there will be Is times Z naught divided by 2, and here there is minus Is times Z naught divided by 2. So again, Is times Z naught divided by 2 can be taken as a common factor, and the remaining terms will be e to the power gamma x minus e to the power minus gamma x. So you can see I have written Is times Z naught times e to the power gamma x minus e to the power minus gamma x over 2. But you know, e to the power theta, okay, plus e to the power minus theta divided by 2. What is this? This is cos hyperbolic theta. Okay. So instead of this bracketed expression, I have written here cos hyperbolic gamma x. And you also know e to the power theta minus e to the power minus theta divided by 2, that is sin hyperbolic theta. So this second bracketed term, that is the expression inside the second square bracket, that will be equal to sin hyperbolic gamma x. So finally you can see that the voltage varies with x in hyperbolic manner. Okay. This is given by Is times Zs cos hyperbolic gamma x plus Is times Z naught sin hyperbolic gamma x. Okay. Now in the similar manner, when you will substitute the value of A and B in the equation for current, then you will get the final result for I of x. You can see I have mentioned here the basic equation for I of x is equal to 1 over Z naught times A e to the power gamma x minus b times e to the power minus gamma. I have repeated this equation. Now let us substitute the values of a and b. You know that a is equal to is over 2 times zs plus z naught. This is the value of a, and times e to the power gamma x. And you have also seen that this constant b is equal to is over 2 times zs minus z naught. Okay. So in this way you can see Ix is equal to 1 over z naught times Is over 2 zs plus z naught times e to the power gamma x minus Is over 2 times zs minus z naught times e to the power minus gamma x. Okay. Now again we will associate the similar terms. You can see when you will take this second term containing z naught in both terms, then 1 over z naught times is over 2 times z naught. So this z naught in denominator and this z naught in numerator will cancel out, and only the factor will remain is over 2 and multiplied by e to the power gamma x times e to the power minus gamma. Here this minus will become plus. So when these two dotted terms I have marked here by dots will be associated, your result will be is times e to the power gamma x minus e to the power minus gamma x over 2. Now I am crossing these two terms. You can see when you will associate these two crossed terms, what will be your result? This will be in fact is times zs divided by z naught times e to the power gamma x minus e to the power minus gamma x over 2. Again you can see this is what? This is cos hyperbolic gamma x and this is sin hyperbolic gamma x. So in this way you can say that I of x is given as is times cos hyperbolic gamma x plus this is times zs, you know, this is equal to vs. So this will be vs over z naught times sin hyperbolic gamma x. So in this way we have relate the current and the voltage with the distance x, or you can say we have obtained the voltage and the current as a function of x, where x is the distance measured from the sending end, that is considering the origin of our coordinate system at the sending end, how we can express voltage and current as a function of x we have obtained in these two equations. The calculation is very simple and I hope you have clearly understand this. Okay. Now the same problem we are going to see, but now our aim is to measure the distance from the load end. It means now we will consider the origin of the coordinate system, you can see in this figure, at the load end, and then we will measure the distance from this reference point. So here you can see again I have shown that this is your load end where voltage is VL, current will be IL and the impedance will be ZL, and this is your source or generator where voltage across it is Vs, current is Is and the impedance is Zs. These are the parameters for the source. This is your source, okay, and this is your load, and this is the characteristic impedance Z0, okay. So result will be same. Now you have to say that if you consider a point here, then this is the distance x. Origin is at the end, at the load end. Okay. So there will be no difference in the equation, but our result will be something different because we are not considering the origin from the at the load end. So actually the term which was representing the incident wave, now you will see that will represent the reflected wave. Okay, because the wave which will travel from load end to source end, that will be now called incident wave, and the wave which will travel from source end to the load end, that will be called the reflected wave. So that will be just opposite. So how we can relate, now you can see. So I have again written the same equation. You can see I have mentioned the same equation number A and B. You know, V of x is given by this expression and I of x by this expression, you know. But as I have told you earlier, that this B times e to the power minus gamma x, this was representing the incident wave in the first case. But in this case, this B times e to the power minus gamma x, this will represent the reflected wave. And A times e to the power gamma x, that will represent the incident wave. Okay, this is the difference. Now boundary condition will also change because you have considered x equal to 0 at the load end, and you know at the load end voltage is equal to VL and the current will be IL, and therefore if ZL is the load impedance, then this VL will be equal to IL times ZL in accordance with Ohm's law. You know, according to Ohm's law, the product of current and the impedance is equal to voltage. Okay. Now we will apply this boundary condition on equation A and on equation B. Okay. When you will apply this condition on A and B, then again you will find the value of A and B. Okay. So let us see. When you will apply this condition on equation A, what you will do? We will take x equal to 0, and you can see when x will be 0, e to the power 0, that will be 1. Again e to the power 0 in second term will be 1. So in RHS there will be simply A plus B. But when x is 0, you can see then this V is equal to VL. So at the place of V of x, now we will write VL. So our first equation will be VL equal to A plus B. Okay. And now apply the same boundary condition on this equation B, and take x equal to 0 in RHS, and in LHS instead of I, now you will write IL. So you can see this will be IL equal to 1 over Z0 times A minus B. Okay. Now again multiply this IL by this Z0, and after multiplication you will get Z0 times IL equal to A minus B. Again you are seeing the same situation. In equation 3 we have obtained A plus B, and in equation 4 we have obtained A minus B. So when you will add equation 3 and 4, B will cancel out and A will be added, that will be 2A, and that will be equal to VL plus IL times Z0. But you know, this VL is equal to IL times ZL. So this is IL ZL plus IL times Z0. You can take this IL as a common factor, and this will be IL times ZL plus Z0. And so A will be equal to simply IL over 2 times ZL plus Z0. So what actually you are seeing here? When we have measured the distance from the sending end, then at the place of this IL there was IS. Okay. And at the place of this ZL there was Zs, okay, and Z naught is at each. Z naught, which is characteristic impedance, that will remain same. So in the similar manner, when you will subtract this equation 4 from 3, then you will get the value of B, and that B will be equal to IL over 2 times ZL minus Z naught. Now again we will substitute the value of A and B in this equation A and B, okay, and then you will get V and I. As we have made the same calculation earlier, so I have not done those algebra, you can do it, and when you will actually done those algebra, you will see that this V of x will be now equal to IL times ZL cos hyperbolic gamma x plus IL times Z naught sin hyperbolic gamma x. And similarly, the page has been turned, but it will be just okay, don't worry, since I am working for a long time on this iPad, so sometimes the page is turned off. So you can see I of x, we will now obtain IL times cos hyperbolic gamma x plus VL over Z naught. In fact, IL times ZL, that will be equal to VL times sine hyperbolic gamma x. Okay. So in this way we have obtained the voltage and the current as a function of x, where x is the distance measured from the load end. Okay. And you can compare these two results, as I have told you that instead of IL there is instead of IS, now there will be IL, instead of ZS there will be ZL, instead of VL is at the place of VS, okay, and Z naught is at each, okay. Now after knowing these two facts, now we are able to find the expression for reflection coefficient. But first of all, we should know what is this reflection coefficient. In fact, reflection coefficient is studied in physics at several places. When you study quantum mechanics, the problem of potential state, problem of potential barrier, then you talk about the reflection coefficient, and the definition is same everywhere. In fact, reflection coefficient, this is denoted by the symbol, this capital gamma. This is capital gamma. Actually I have written modulus of capital gamma, okay, it because its magnitude is taken, and this is defined as the ratio of amplitude of reflected wave and the amplitude of incident wave. It means when you will divide the amplitude of reflected wave by the amplitude of incident wave, you will get a number, and that number is called reflection coefficient. In case of light wave incident on a surface, it depends on the nature of the surface. Similarly, here this load end behaves like a reflecting surface, and how much voltage or how much current will be reflected will be in fact will move in opposite direction. That is measured in terms of this reflection coefficient. If you say that this gamma is equal to 1, it means there is a complete reflection of the wave. But if gamma will be 0, it means there will be no reflection. No reflection means there will be a complete absorption of wave. Okay. So this gamma is the measure of the degree of reflection. How much wave will be reflected from the load end, that is measured in terms of this reflection coefficient. Okay. Now actually if your aim is to find the expression for this reflection coefficient, definitely you have to know what is actually the amplitude of reflected wave and the amplitude of incident wave. You have already seen there are incident and reflected wave in terms of voltage and current variation. So we will separately calculate the reflection coefficient for the voltage wave and the current wave. But before that, we will have to cast those equations for voltage and current in proper form so that it will represent a wave and we can decide what are the amplitude of that wave. And for this, as I have told you earlier, that in our calculation the quantity gamma which have occurred earlier, this is actually called the propagation constant. Okay, and this propagation constant in general is a complex quantity, so it will have actually the real and imaginary parts. So I have expressed this gamma as its real part alpha plus its imaginary part beta, that is iota of beta. You can write here j because I have earlier write j instead of I. Okay. In fact, this alpha is known as attenuation constant. How much the amplitude will be get attenuated? It increases with increase in distance or it decreases with increase in distance. That is determined by this parameter alpha. It means amplitude, how amplitude will be affected by the distance, that is determined in terms of alpha. So this is called attenuation constant. Okay, and this beta is the phase constant or phase factor. Okay, now let us see v of x. You know this is given by a times e to the power gamma x plus b times e to the power minus gamma x. But you have now considered this gamma is equal to alpha plus j beta. Okay, so let us write here j. So this is a times e to the power alpha plus j beta times x and plus b times e to the power minus alpha plus j beta times x. Okay, now we will simplify this RHS of this equation a little bit so that we can cast this equation in a proper form so that we can decide what is the amplitude and what is the phase factor of the wave. Let us see. If you will write this e in e to the power alpha plus j beta times x in this form, this will be a e to the power alpha x times e to the power j beta x. Okay, and the second term can be written as b times e to the power minus alpha x times e to the power minus j beta x. Okay, in fact this first term, you know, this represents the incident wave and this second term represents the reflected wave. Now e to the power j beta x, the presence of j actually makes this function oscillatory. So this is the wave part, or you can say this is the phase part of the wave. And this a times e to the power alpha x, this is amplitude, and you can see this amplitude is not constant. It varies exponentially with x. So this constant alpha is called attenuation constant, because when this wave will travel in the transmission line, its amplitude will not remain constant. It will either increase or it will either decrease with increase in x. In this incident wave, you can see with increase in x, amplitude will increase because E contains a positive power. But in in case of reflected wave, you can see that the amplitude is b times e to the power minus alpha x. So with increase in x, this amplitude will decrease. Okay. this amplitude will decrease. You can see when we will talk about the amplitude of the incident wave. Let us say this is AI, this is amplitude of incident wave. When x is equal to 0, then you can see this will be A. But with increase in x, this will increase in this manner. But if you are talking about the reflected wave and you consider that its amplitude is AR and plot a graph in against of x, then you can see when x is 0, then it will be equal to B, and with increase in x, it will exponentially decrease. So this is attenuation, okay, and therefore alpha is called attenuation constant, okay. So I have mentioned it here. You can see that A times e to the power alpha x, this is called amplitude of the incident wave, and B times e to the power minus alpha x, this is amplitude of the reflected wave. Now after knowing the expression for the amplitudes of incident and reflected wave in accordance with the definition of reflection coefficient, now you can easily obtain the reflection coefficient. Since we have simplified the equation for the voltage, that is voltage wave you can say, so I have written here the symbol gamma V. It means this is the reflection coefficient for the voltage wave, and that will be equal to what? That will be equal to amplitude of reflected wave divided by amplitude of incident wave. But you know, the amplitude of reflected wave is B times e to the power minus alpha x, and amplitude of incident wave is A times e to the power alpha x. So this will be simply B over A times e to the power minus 2 alpha x, okay. But you have seen what are the values of A and B. We have seen that A is equal to Is over 2 times IL over 2 times ZL minus Z naught, okay, and sorry, not minus but plus, and B is equal to IL over 2 times ZL minus Z naught. You have seen earlier. You can see the values of A and B. These are the values, okay. So when you will substitute the values of A and B, IL over 2, you can see these are the common factors, so they will cancel out, and therefore the magnitude of the reflection coefficient for the voltage wave, that is gamma V, that will be equal to ZL minus Z naught over ZL plus Z naught times e to the power minus 2 alpha x. So this reflection coefficient is not constant. It also depends on x, and you can see this reflection coefficient decreases with increase in x exponentially. So when you will plot a graph of this gamma V, modulus of gamma V in against of x, when x will be 0, this exponential factor will be 0, and this gamma V will be equal to this much. This will be the value, okay. This will be the value. I am not writing here. This will be ZL minus Z naught over ZL plus Z naught. This is less than 1, okay. And after that it will attenuate, it will decrease, okay. Now in the similar manner, when you will consider the current equation instead of the voltage equation and try to find the amplitude of the incident wave and the reflected wave. This is just a homework for you. You must simplify the current equation, that is equation for I of x, okay, taking gamma equal to alpha plus j beta. Then you will see that the amplitude for the the reflection coefficient for the current wave will be equal to this much. This is minus ZL minus Z naught over ZL plus Z naught times e to the power minus 2 alpha x. But you know, this, apart from this minus sign, the remaining factor is simply gamma v. So a very important result we obtain here, that the reflection coefficient for the current wave is just equal and opposite, or you can say it is equal to the negative of the reflection coefficient of the voltage wave. Okay. Now let us consider two particular situations. If you consider that our load impedance ZL is exactly equal to the characteristic impedance Z0, then what will happen? You can see, if ZL is equal to Z0, you can see the expression for the reflection coefficient, either for the reflection coefficient for voltage wave or for the current wave. You can see this will be equal to 0. I have written here gamma v, that will be equal to 0. In fact, IL will be gamma I will be also 0. And if ZL is not equal to Z0, but you consider that X is equal to infinity, it means from the load end our test point is far apart, then again you can see, due to the presence of this factor e to the power minus 2 alpha x in the expression of gamma v, when we will take x equal to infinity, then this will be e to the power minus infinity, and that will be equal to 0. And therefore, this gamma v will be again 0. So this reflection coefficient is 0 in two conditions. First condition is what? When the load impedance and the characteristic impedance are equal, then there will be no reflected wave. Reflection coefficient is 0, it means there is no reflected wave. But if ZL is not equal to Z0, but our test point is far apart from the load end, then again this reflection coefficient is 0. So again there will be no reflected wave. So if there is no reflected wave, then what will happen? It means there will be a complete absorption of the incident wave. So I have mentioned here, you can see it means in both cases no reflected wave is produced. Okay. Instead, the incident wave is completely absorbed. Okay. So I think this session was definitely interesting to you, and when you will watch this video and write down these things in your notebook, that will be a very good notes for your examination purpose. Okay. Thank you very much.